Hi, thank you for joining me in this poster presentation for the work titled Development of a Lead-Free Galvanic Sensor for the Quantification of Inspired Oxygen in Medical Applications. My name is Gilberto Martinez Saucedo. I am a project engineer at Center of Engineering and Industrial Development at the city of Santiago, Querétaro, Mexico. So let's start briefly with the summary of this work. Well, we studied commercially available galvanic oxygen sensors for medical applications, and what we found is most of them are lead-based. So in this work, we developed a different type of sensor which uses a copper anode for a lead-free galvanic sensor, and we use an electrochemical array where we also used a silver cathode for the reduction of oxygen. And with this, we determined we quantified the fraction of inspired oxygen in a mechanical ventilator system. So for the introduction, we know that lead is a very malleable metal, also very low cost and has a high density, and it has been traditionally used in oxygen sensors. The high density is important because we can use a small volume of lead but still have a high potential or lifetime potential of the sensor. Nevertheless, as you all know, lead is highly toxic, and in a manufacturing process we have to be very careful of contamination. Also, when the sensors are being disposed of, we need special handling. Now, especially in the European Union, recently there have been alternatives considered for medical applications, and well, lead has become a center of discussion to migrate to other kind of technologies. So in the future, it is desirable to have a lead-free, more environmentally friendly devices. There's not many information regarding these galvanic oxygen sensors in the literature, but we know that some metals such as copper or tin or antimonium or aluminum may be used as anodes. So in this work we researched a copper-silver electrochemical pair, and for this device we also had to use a semi-permeable membrane for the diffusion of oxygen and its quantification, since we have as a central part of the electrochemical reaction, reduction of oxygen and oxidation of the anode, in this case copper. Okay, so let's discuss the methods we use for this work. We manufacture several components for the testing of these assembled galvanic oxygen sensors, as shown here in the figure, where we use copper and silver metal electrodes with at least 99.9% purity, and these were used as anode and cathode respectively. We also prepared a conducting electrolytic solution with potassium hydroxide of 10%, and we used commercial PTFE and PTFE PHEFE thin film membranes, which were pre-assembled on a holder ring for oxygen diffusion in the sensor. Now this holder ring was pre-assembled with a machine press to ensure gas-liquid hermeticity of the solution inside the cell. We also characterized these sensors using a Keithley multimeter with a data acquisition interface with LabVIEW software. And we proceeded with characterization of the sensors, where we determined the ideal resistance for the cell operation. And we also determined components for temperature compensation, which were assembled in a PCB for the output voltage signal conditioning. Finally, these sensors were tested in a real setting, which was a mechanical ventilator system, using a fluke gas analyzer as a reference. Below, we show the reaction for the anode, where we have the formation of copper hydroxide ions, and the reaction for the cathode, where we have the reduction of oxygen in water. Now for the results of our work, we had that sensor voltage output yields a mean value of 745 millivolts, and this is after self-stabilization. So we manufacture several sensors and obtain these values. Now the optimal resistance for the signal conditioning was 860 ohms. After this resistance optimization, the voltage of the sensors was plotted against time, as you can see in this curve. And you can see that with different oxygen percentage values, the voltage increases, just as described by the Nernst equation. And we can observe that the increase in voltage is linear as a function of the oxygen partial pressure that diffuses through the semi-permeable membranes in the electrochemical cell. Now, the voltage increase obeys or is consistent with a exponential decreasing type function of voltage versus time. After this testing in the laboratory, we transferred the sensor to a real setting, which was a mechanical ventilator system, where we used defined parameters such as flow, volume, and pressure, as you can see here in the figure. And after this testing in the mechanical ventilator system, we found that there's a linear relationship between the voltage value and the fraction of oxygen, where we used the commercial gas analyzer as a reference. We found that there is a linear correlation with a value of 0.9993 for a total of 3 scans. Now we also determined an important parameter for these oxygen sensors, which is stabilization time. And we determined the value of the voltage at 90% versus the fraction of oxygen, where we estimated that this value is of 65 seconds, which is comparable to other comparable lead-free commercial sensors, which there are not many of. Finally, we determined the repeatability of these sensors in the mechanical ventilator system. Here we made measurements after 7 days, and we can see here in the figure that there is repeatability in this voltage value, and this is mainly due to having an optimized temperature compensation through thermistors. Now, if we have a deficient thermistor arrangement in the PCB conditioning signal card, we have a deficient temperature compensation, and we do not observe this signal repeatability. We also determined an important parameter of the sensor, which is operation lifetime, through the Faraday's electrolysis equation. And we determined that the estimated lifetime is 3.7 years at 100% oxygen value. Finally, we would like to thank CONACYT for the sponsorship of this project. And we also would like to thank the Department of Manufacturing and Mechanical Engineering at CIDESI for their great support on sensor design and assembly.